Hi, I'm Jim Pasmore with Analytical Services and Testing, and today I'm going to give you a demonstration of this new Niton XL5 Plus from Thermo Fisher Scientific. This is the smallest, lightest, and fastest, and most accurate analyzer I've ever used in an X-ray fluorescence analyzer. I kind of compare it to a cross between a Porsche 911 and Land Rover Defender because of its speed and size, and yet it's extremely rugged. Nice metal case, and it looks industrial, even though it's elegant in its design. It's got a little strap so you can put it over your wrist in case you're climbing a ladder or doing something like that in a refinery. You've got it safe in your hand, and even if you happen to let go of it, it's not going anywhere. So in addition, it's got a macro camera, so I can take a look at various things that I want to shoot and take a picture of it. It's got a micro camera, so I can see the exact spot I'm measuring. And what I'm going to show you first is I'm going to show you one of the most difficult applications for an analyzer like this or any XRF handheld, and that is extremely low levels of elements in an ion matrix for applications like API 571, where you've got to look at residual elements such as chrome, nickel, and copper at very low levels, or maybe microalloying elements, which are down in the 01, 02, 004 type ranges. So we'll start with a BS15A, which is the one I use for testing for microalloying elements. And I will mention that if you notice on the screen, it says General Metals in the lower right, LASCF, low alloy steel Cal factors. What I've done is I've taken the factory low alloy steel model, which is designed for a wide range, and I've tuned it in specifically to low alloy steel, where it's a very low level of alloying elements. And what that gives me is much more accuracy because it's got the precision to do these things really well. All we have to do is make sure that we tune it into the accuracy, and you'll see that as we take a measurement or two here. I'm going to shoot the BS15A first. I've got it set for 20 seconds on what's called the main filter, and I've got it set for 30 seconds on the light filter. Now, the main filter is the one that measures the heavy elements, such as the ones you're seeing on the screen now, with the exception of what's called LEC. LEC is light element content. That's the elements that we have to measure with the light filter. Elements like aluminum, silicon, sulfur, phosphorus in the case of iron-based materials, or even magnesium in the case of aluminum alloys. So now we've switched to the light filter, and we're seeing on the left the element and its symbol, in the middle the percentage measured, and on the right the 2 sigma or 95% confidence limits. And the key with XRF is if you're looking for light elements and if you're looking for very small quantities, you measure a little longer, because the longer you measure, the better the precision, and therefore the better the accuracy. So let's take a look at the results compared to the certificate of analysis for BS15A. And here we see BS15A. Manganese is certified at 1.12. We're seeing 1.18. We'll go down to what's on the screen. Chrome is certified at 0.044. It's 046. Copper 042. It's certified at 0.03. Let's see, what have we got on there? Niobium. We'll have to go down a little bit for niobium. Let's get some more of these elements on the screen here. Okay, moly is certified at 008. It's reading 008. What did we do? Copper. Yeah, 03, 042. Let's scroll down for some more elements. Phosphorus, 016, it's reading 03. Zirconium is 002, it's reading 019. We looked at moly already. So other elements that are below the detection limit, nickel, it says that it's reading of 024, but it's below the detection limit, so we can't count on that. The certified value is 029. Vanadium's below the detection limit at 008. It's certified at 0012, and so on. So we're not going to be too concerned about trying to get those elements that are below detection limit. If we really want those, we would measure longer. And the longer we measure, every time we measure 4 times longer, we double our precision. And therefore, our limit of detection improves as well. So we might see some of those popping on the screen if we're willing to measure longer. So now let's take a look at a pipeline alloy. That's another really important application where we have very low levels of materials, of elements, that is. And let's take a look at the 5LX42A, which is an important one for the pipeline application. And I have one here, a 5LX42A. Let's take a shot of that. Same thing. We're going to do 20 seconds on the main filter. We have higher precision typically for the heavy elements, so we can measure less time. And then we're going to do 30 seconds on the light filter, and that should give us the result that we need in general. You won't have to measure longer than that. If you don't need the light elements, such as aluminum, silicon, sulfur, and phosphorus, you're done after the 20 seconds. Now we're going to continue on to the 30 seconds, and you'll see that at the end of the 30 seconds, we'll compare that to the numbers on my composition chart, which I've taken from the certificate for a whole number of standards that I have in my supply here. So at 50 seconds, it's going to stop. I have it programmed to stop at 50 seconds. And there it is. And let's take a look at the numbers. So let's scroll over here. So we're looking at chrome is certified at 0.18. It's reading 0.183. Copper is certified at 0.123. It's reading 135. Manganese is certified at 1.02. It's reading 1.03. Let's scroll over some more. Moly is certified at 050. It's reading 054. Niobium is not on the screen. Let's scroll down a little bit. Okay. Nickel, 087, is reading, certified at 078. Silicon is certified at 0.19. It's reading 05. Let's see, 046, yeah. Phosphorus is 015. It's reading 008, almost 01. Zirconium is not of interest to me. I'm not going to bother with that. Niobium is certified at 002. We're reading 001. So as you see, the values are all excellent compared to the certificate, and you can certainly go out and do pipeline surveys and expect to get really good results. So we're going to switch now to another application. We're going to switch to quick sorting. This is an application that you'll see typically in the scrap yards. So let's go ahead and take, for example, some of the most important alloys in scrap yards are stainless steels, aluminum alloys, and then you get into the high value like the nickel base and sometimes coppers and titaniums and so on. Now, I'll start with the aluminums because that's an area most people have issues with in terms of the ability to sort quickly. So I'm going to switch my model to the general metals. Sorry, I picked the wrong one. Let's do that again. There it is, general metals. Okay, this is the factory calibration, and this is the one you'll be using most of the time for almost everything. Now, what I will say is that there's 2 libraries in this analyzer. One is called the factory library, and what I've done is because the factory library has so many varieties of aluminums in there. And because those varieties are so close together, what I've done is I've set up what I call the common aluminums in the library so that you can do quick sort with the main filter and not have to use a light filter for most everything you're after in the common range. If you have something that isn't in the common range, we'll talk about that, but basically you just switch to the factory library and it'll pick up those others. So let's start with the ones that are the three aluminum alloys most people are sorting and have most trouble with because they're so close in chemistry. Here is a 1100. That's mostly pure, but with some iron in there. And there it is. And you see that came up in less than a second. I couldn't quite release the trigger quick enough. Here's a 6061. That also is difficult to sort in general. And here's a 6063. And you can see how quick it is with this library. Now I can go on and measure all the common alloys. 2018 has a bit of nickel in it, so that pops right up. 2024 is one of the most popular aircraft alloys. Almost everybody's sorting it based on the copper. And 3003, that's got manganese in it. And so it sorts real quick based on the manganese. You can see that at 1%. Here's the 4032. This is a high silicon, but because other elements characterize it, I don't need to wait and do the light filter because I get 4032 based on the chemistry of the other elements. It's like a fingerprint for it. If I wanted to hold the trigger longer, it would switch over to the light filter and I would measure the light elements in 4032. Here's a 5052 characterized mainly by magnesium. Now, magnesium is a light element. So can I get this without going to that? The answer is yes. Again, it's the fingerprint that does it, the fingerprint of all the other elements. So we don't have to go to the light filter to know that's a 5052. Now, if I had a 5056, which is very similar with the exception of magnesium, I would have to hold the trigger another few seconds to get the difference in magnesium and to sort those two. Here's a 7075. This is your high zinc and copper both, another aircraft alloy, and one very similar, so close that the only difference is 0.1% in zirconium in terms of the recipe for these two alloys. And you'll see it picks that zirconium up right away. It's about 1/10 and it's reading 0.98. So we're pretty satisfied that we can do all the aluminums quite quickly. Let's go to some money-making alloys like 316 and 304. These are two of the most popular stainless steels in the world. They're both considered to be like an 18-8 chemistry, although the 316 has a little higher nickel. Instead of 18 chrome, 8 nickel, it's got about 17 chrome and almost 10 nickel. But the big difference between that and the 18-8 304 is the moly, which is 2%. Now take a look at the 304 when I shoot this one. And what you'll see is it does come up with the typical 18-8 chemistry, but moly is very low. And that's how we know the difference. Now we've got some stainless steels that are used quite widely in the refineries where they stabilize the 304 with titanium. So they call that a 321. And if I shoot the 321, what you'll see is it'll say, oh, it's very close to a 304, but whoa, there's titanium in there. And therefore it's a 321. Otherwise, it's very similar. Let's go to a 347, another niobium stabilized 304, so to speak, but characterized by that niobium as a 347. And there's the niobium. Now, this is a 347H, so it's high carbon, and therefore, when you multiply the carbon times 5, you get the niobium content, and it's higher. Here's an interesting one. This is a nitronic 60, which is high silicon. Now, do I have to hold for the light filter to get silicon? Yes, I do. But the light element content, LEC, automatically comes up once it identifies it as nitronic 60, and I don't have to measure it directly unless I want to know the exact amount. It says typically it's nominally at 4% LEC, light element content. That's your silicon content. And here's a 303. Now this one is interesting because it's a free machining 304, so to speak, similar chemistry to a 304. And the only way you can tell these two apart is by the light element content. And I'm not measuring that right now. So if I were to set it up so it would measure on the light filter, it would pick up that 0.3% sulfur and immediately switch to a 303 identification. That's just a matter of whether you want to take the time to do that or not. Okay, last one in the stainless steels. Here's a 310. This is a real money maker for the sorting business because it's high nickel, and nickel is quite valuable. And there we see nearly 20% nickel. So let's go to even more value. Here's pure nickel. Depending on the price of nickel, this can be a really valuable alloy. And of course, it pops up as what's called nickel 200, which is pure nickel. Here's a Monel alloy, which contains high copper in the 30+% range. And there's that high copper, slightly less than expected, but it's still in the range of an alloy 500. And here is a 625. This will be the high nickel value, again, about 60%. And there it is, 625. There's a 718. This is a really important alloy in the aircraft industry because it's a real high temperature alloy. If you look at that moly and niobium, that really sets it up as a high temp. And waspaloy used in the hot side of the engines in aircraft. This is a really popular aircraft alloy. And then we've got something like Hastelloy X, very ubiquitous. There it is. Last one in the nickel-based alloys and cobalt-based alloys will be a CMX, in this case, CMSX4. CMSX stands for Cannon Muskegon Single Crystal, and it's grade 4. And this will have exotic elements like tantalum and rhenium. And there you see your tantalum and uranium popping up. A very expensive alloy. Let's switch over to the coppers. There's a CDA 110, pure copper. So there it is, very quick. And that's the story on the XL5. You can use it for a wide range of applications, whether it be in manufacturing, incoming QC, outgoing testing for quality. Before you ship something, you can use it in positive material identification for extremely fast sorting in the scrapyards. It's so versatile. It's so usable. And everything about it is just ideal for what I would want to use it for testing services. This would be my instrument of choice. Even though there's less expensive ones on the market, nothing comes close to this in terms of performance. Thanks for watching.